back Carl's homework. So do not, this is Carl's stuff. If you're turning homework to me, put it in. This is Carl's exam, my exam. Carl's homework and my exam. So turning homework in over here.
For the last exam, is that open notes?
Yes. So Matt, are you bringing that back? Yes. Okay. So yeah, the last exam is open book, open note. It's not open internet, right? So don't be coming in here with a laptop and like Googling away. But it's open printed material, I guess. Let's put it that way. You can bring in any textbook or printed material you want.
If we're not the internet.
Yes, you may. All right. Any other questions on the exam? So as I said in my email, don't take that as an excuse to not study. Don't figure like, oh, I'll just, it's all be in my notes, I'll just look it up, I'll figure it out. No, you need to study. I mean, my intent was doing this homework would be good studying. But make sure you understand this. And if you, I would highly recommend looking at my homework solutions that I'm going to post to Moodle. Look over them, all of them, and make sure you understand it. And if you don't understand it, you can ask me. We'll be around next week. All right, probably every day, and we'll be grading. And so if you want to send me an email and say, hey, I don't understand something in your homework solution, can I come by? I'll say, sure, we'll work out a time and we can talk about it. All right? So we can get more help before the test. Okay, so on to Isaac's request. Yeah, I'm pretty sure it's correct. So, Lighting Disc Part 1, this story asks you to set up the 4 equations for a numerical solution. And so the first 3 should be trivial, and so I don't think I'm going to waste time on them. So the first 3 are the conservational momentum in the X, conservational momentum in the Y, and then conservation of kinetic energy, because this is the last collision. All you have to do is find the density of steel on the internet or wherever, find out how much each little disc weighs, and then you have mass 1 and mass 2, and I gave you everything. I gave you the initial velocity. So you just plug those into the equations, that's all there's to it. Any questions on that, the first 3? No? Okay. So the last one is where, as I say, is where the trick is. And so what you need to do is get a position vector as a function of time for each of the 2 disks. This is the part that's a very, very simple integration. And so the first one, disk 1, I said it was going at 3 meters per second in the X, and 1 meter per second in the Y. So we want to know positions, so we're going to integrate it. We're going to go from velocity position to integrate. So we're integrating a constant. Remember at the end of the lecture on Monday I said, what's the integral of a constant? That constant times whatever the variable is. The integral of 3 with respect to time would be 3t. And indeed, here we are, 3t. So for our first, want to give me your markers in that? Yes. So for the first one, it's going to be 3t plus a constant. And so the constant being, take a book, plus constant, so that constant is the initial position, which I also gave you. So we have P1, a vector of t, and so it equals our 3t, this is our integration we did. We took 3 and we integrated it. All right, and I expect you to do this kind of thing. Plus the initial position of 0.06, and this is in the I direction. Everything here is in meters, and so I'm just going to save myself time writing m after every single term, and I'm just not going to. That would be me on my mind. All right. Plus, we have the j component. So it was 1 meter per second in the j, so we integrate 1, we get t. So we have t plus the initial position in the y, which is 0.2, plus 0.2 in the j direction. There we go. There is our position vector as a function of time. Okay? That was calculus. It was very easy calculus, but I do expect you to do it. Alright? I do expect you to be able to do it. And the test is probably going to be a little harder than this. It'll be more on the order of can you integrate x squared. Maybe that kind of challenge. So I'm expecting everyone to be up to. You may also conceivably, the hardest it would get would be what's the integral or derivative of like cosine or sine. I'm not going want to bring in a table of integrals and derivatives, that's fine. Well, find it on the internet, table of integrals, Google it, print it off, bring it in, that's
What
fine.
equation do you want them coming from? Did you show us what you're doing?
This is the integrate, that's what I was just saying. It came from this right here. I got this disk one, the distance and velocity. I integrate these. To get from a velocity to a position, I integrate.
So is that, did you give us the fourth equation? Because I don't remember that. I know you're saying you gave us the information.
All right, so here's what I'm
I
saying.
didn't know what, how to even make an equation.
So,
I didn't know. I didn't know how to integrate. I kind of applied.
Jordan, here's the thing. I expect you to be able to apply the stuff I've taught you. I went over a number of times things with positions, with my sailboat, and my other little examples. This is an application of that. It's an application. I'm not going to spoon feed you every single application before I then ask you to do it. I mean, when you go out in the real world, are you going to cover every single kinematics problem you ever see previously in this class?
I probably won't be doing kinematics.
Well, it's not that you're in the class though, it's required for your program.
Yeah.
You know? And there was another student asking me a similar thing. It's like, you didn't do this in lecture. It's like, yeah, I know. This is an application. You know, I'm not going to do, you know, it's like, hey, you never did this problem with bicycles. You never did a problem with bicycles. How can you do that? You did something with bicycles. It's like, yeah, I didn't do bicycles. I did sailboats, and I did rockets, and I did footballs, and I did Dukes of Hazzard, and I did space probes, but you're right, I never did bicycles. What was I thinking? All right? So, the essence of this is just, okay, before we get into the guts of it, let me talk about the essence of it, is you have, for the fourth equation, what you essentially need is the angle of contact. And that's what you don't have, right? You need it. Everything else for the fourth equation you already have. Either it's one of the things you're solving for, it's the V1 or V2 or whatever, or it was given to you as the U1 or U2 velocities. The only one in that equation, everybody knows what equation I'm talking about, tangent theta equals whatever. The only thing you don't have, what? Yeah, that one. The only thing you don't have in there that isn't one of the things you're solving for, because you're solving for the V, the various V's, is the theta. And so all of this stuff, the initial positions and the velocities, you all find theta. That's what you're trying to do here. Because you have these two things, there's the one that starts sort of up here and the one that starts up here, and they come down, they come sort of like that. I'm trying to do this from your perspective, and they hit. This one's coming down -9 in the y, and +2 in the x, so it's coming down like that. This guy's coming over here with a velocity of 3 in the x and 1 in the y. Anyway, so they come down and they hit each other. And what's the angle between their centers? That's what we're trying to figure out. That's what we're trying to figure out. And so the only way you're going to get this is by having the position vectors as a function of time, what we're doing here, okay? And then you're going to have to find what time is it when they are R1 plus R2 apart. So that's when they collide. When they're two radii, when you add the two radii, that's the distance they are apart. That's how you're solving this problem. So what we're going to end up with is we're going to want to know the difference between their positions. How do you find the difference? You subtract things. Okay, like if I were to say Tom is 10 miles north of me and Mary is 7 miles north of me, how far apart are they? Subtract 10 from 7. You get -3 and say, oh, well, I want a distance, so it's absolute value and it's 3. Or you go the other way, 7 from 10, you again get 3. All right, you want to know the difference between things, you subtract them. So we're going to take our P1 of T, and we're going to subtract, and say it doesn't matter what order you do as long as you take the absolute value of it, of T. We're going to subtract those. That's the distance between them at any given T. And we're going to set that equal to our distance. And so we're going to take the magnitude of it. The magnitude, that's how long that vector is. This is, you add and subtract vectors and you get another vector. All right, so this is going to be a vector, a distance vector. We're going to take the magnitude of it. And this needs to equal the distance between the centers, which would be the 0.05 meters. Okay? 2 centimeters plus 3 centimeters. Those are the 2 radii. So we're going to set, that's what we're going to do. Then we're going to solve this for T, which is quadratic formula. All right, and that gives you a T. You then go back to your original P1 and P2 little vectors here. You drop that time in, you get positions in terms of x and y. You get like, okay, here it is in the x, here it is in the y. Draw it up, and then it's just like what we did do in lecture, and you find the angle. Okay? So this is what you're doing. And this is an application of all the vector stuff I've been talking about.
Then people would put PP vector would be
Yeah, I mean, I've done this one, and yeah, the second one's not any harder. So now I'm going to rejoin where I was.
As far as the quadratic formula, will you accept either answer?
No, one's correct and one's wrong. You know, when you think about which one's right and which one's wrong, we'll talk about it. We'll get there. We have time. I believe I have time, hopefully, to finish this one problem at least. Okay. So P2 of T, again, we're going to integrate, and so we end up with 2T plus its initial position of 0.2, and that's in the I direction, plus integrate again, negative 9T plus 1.2, and this is in the J direction, so there are two vectors. We are now, as I said, we're going to subtract them, so I'm going to say this is a distance vector, the D of T. I'm just going to subtract one from the other. I'm subtracting D P2 from P1, and so I end up with, I'm just going to get T, so 2T, 3T minus 2T, so T minus 0.14 in the I direction, plus 10T, the 1T minus the negative 9, so 10T minus 1 in the J direction. That's my distance vector. So, that. And so now this is what needs to equal, the magnitude of this distance vector needs to equal my 0.05 meters. Okay? And when the way you find the magnitude of the vector is Pythagorean theorem, essentially. You square the terms, add them together, take the square root. To save having to take the square root, you can square both sides. So what I'm going to do here is I'm going to say I want the 0.05 meters to equal the magnitude of D. When that is true, D of T. When that's true, I probably found my correct T. Alright? I want to avoid having to take the square root, so I'm going to square both sides. So then what I have is I have 0.0025 meters squared equals magnitude of D of T squared. So now I don't have to take the square root, so I'm squaring. Okay? So I'm going to take this guy and I'm going to square it. Square each term. Alright? So hopefully everyone can do this. This isn't even talking like sort of trig. When you would have taken this. I'm sure when they covered English math for a second. But everybody should be able to do it. Something like that. So we square this. So what do we get here? We get T squared, and then it's going to be minus 0.28 T, and then plus